So today our mathematician spotlight is Dusa McDuff, who's a mathematician at Barnard College in New York City. She's originally from Scotland, and she's actually older than most of the mathematicians I've been spotlighting. She's right now 72 years old. She's a very eminent mathematician. She's gotten lots of awards and honorary degrees and that sort of thing. And she studies symplectic geometry and topology. So symplectic geometry and topology, I've decided not to talk about what it is, but it only works in even dimensions. So like 2 dimensions, 4 dimensions, that kind of thing. 2 dimensions we got, right? 2 dimensions, here it is. But what about 4 dimensions? Maybe 2 dimensions isn't, you might not have everything you need in 2 dimensions. You might want to go up. So how do you visualize 4 dimensions? It's a crazy idea, right? So here are a couple ways of visualizing 4 dimensions. So here, this point is 0 dimensional. Here's what I'm going to do. I'm going to double this point. Now there's 2 of them, and I'm just going to pretend like it made a trail, like I dragged it over. I doubled it and then I dragged it over. Now I'm going to draw a second picture of this. But I'm going to pretend that when I pulled this, the points sort of dragged themselves. So the point was 0 dimensional, the line segment was 1 dimensional, and now this square is 2 dimensional. So if we make a copy of this square, and then we pretend like each of the vertices drag themselves, we get a cube, which is 3 dimensional. And then the last thing to do, and I'll do another color so we don't get confused, is draw a second picture of a cube. So here I'll just draw the same cube again, but in yellow. Okay, there's my cube, and now pretend like every vertex dragged itself when it was going. So these guys all dragged themselves. And that is a 4-dimensional cube. Pretty neat, right? Yeah. So whatever it is, so it's very hard to tell what's going on if you just look at this picture. But the idea is to construct it, to start with the 0-dimensional thing, use it to construct a 1-dimensional thing, use that to construct a 2-dimensional thing, use that to construct a 3-dimensional thing, and then somehow imagine what it would mean to use that 3-dimensional thing to construct a 4-dimensional thing. Crazy, right? Right, it's hard to imagine where it exists. It doesn't exist in 3 space, like we do. I mean, it's even hard, this white cube that I drew is a 3-dimensional thing that I'm trying to draw in 2-dimensional space, so that's even hard. Than this, you have to somehow imagine that we've drawn this 4-dimensional picture in 3-dimensional space. So this is like 4-dimensional cube. That's the idea. Yeah? Okay. So something about symplectic geometry would involve 4-dimensional space. That's the idea. Okay, so in the previous lecture, we discussed triple integrals. So triple integrals are like for finding the total mass of an object. So you imagine that you have this solid and it has different density at different points. So you want to know what the total mass is. Or maybe you just have a crazy shape and you want to know its volume. It has the same density everywhere. So the thing that we'll do today is talk about the limits of integration. How to use the solid object to determine the limits of integration. So our first thing is to set up the integral. So set up the limits of integration for the triple integral over R of e to the x z squared times y times cos xy plus 3 dv, where R is the solid half ball. So you take the unit sphere, you cut it in half using the yz plane, and you take the part on the positive x side. So I'll try to draw that. So here's a unit sphere. There it is. And you imagine that it has, let's see, the x-axis coming out this way, the y-axis escaping from the back, the z-axis at the top, and then here's the negative y-axis and the negative x-axis. And then you imagine that you slice it with the yz plane. So the yz plane is like this plane. So somehow we slice it like this. And we just want the forward half. So like this part here. So, yeah. Okay, so we want like the right half of this picture. Yeah, so this is our region R. Okay, good. So, and let's do the order, let's see, dy, dx, dz. Okay, so we want to set up an integral. Let's see, where z, so let's see, dy, dx, dz, so dz is on the outside, so z goes from something to something, and then x goes from something to something. And then finally, y goes from something to something, and then we have our integrand, e to the x squared, xz squared, y times cosine of xy plus 3, and then dy, dx, dz. Whew, that's what we want. So our goal is to find these limits of integration. So let's forget about the innermost part now and just set up the limits of integration for this thing. So I like to think of this part as like the shadow plane. So you're looking at the shadow of this solid in the xz plane and trying to describe it. So the shadow plane is the xz plane that kind of cuts the sphere here. So let's draw a picture. So with our orange solid, we only get half of a circle in this xz plane. So here the y-axis is coming out toward you, so you can only see half of the thing. So we want to somehow describe this region in this order. Let's see, so that's our goal. So this is just like setting up a double integral, which we've done before. So if we are integrating with respect to x, z is a constant, so we pick our favorite z, and we go across. So we're going here from x equals 0 up to x equals something. We just have to solve for it. So this is a unit circle. This is like x squared plus z squared equals 1. So if we want to solve for x, we get x squared equals 1 minus z squared. So x is the square root of 1 minus z squared. And maybe it's positive or maybe it's negative. We should look. Okay, on this side it's positive and on that side it's negative. So we want the positive side. So x is going to go from 0 up to the square root of 1 minus z squared. And then, okay, that'll be good for all the way at the bottom to the top. And then z goes from -1 to 1 to pick all that up, because this is a unit circle, unit sphere. So z goes from -1 up to 1. Okay, so that describes like this plane in the middle. That's what we've drawn over there. And now you have to say, okay, which y's do I need in order to stay in the solid? So the way that I like to think about this is that you have some point x comma z in your shadow plane here. So maybe it's this point right here. So I'll draw it in this picture also. There it is. And now you take a line in the x direction. Sorry, in the y direction. The y direction, which is what we need to define, that passes through this point. So it starts way back here in the back, and it's not touching the sphere at all. And then at some point, it goes in. Like back here, it comes into the sphere, or the solid ball. And then it stays in for a while. Now it's touching our shadow plane. Then it stays in for a while, and then it pops out, and now it's out. Okay, this is not my most parallel line that I've ever drawn. How about that? That's better. Okay, so you ask, when does my thing pop into the sphere, and when does it pop out? So, well, that's just solving the sphere equation for y. So to solve for this guy, we know that for the unit ball, x squared plus y squared plus z squared equals 1. So let's solve for y. Y squared is 1 minus x squared minus z squared. So y is plus or minus the square root of 1 minus x squared minus z squared. So again, we should figure out, like, is it the plus or is it the minus that we want? But we actually want both, because, let's see, I guess we should imagine that it's coming from the negative direction and going to the positive direction. So I should have been going this way. So it comes in on the negative part of y, and it comes out on the positive square root of y, and in the middle we have where y is 0, here on our shadow plane. So this should go from y equals negative square root of 1 minus x squared minus z squared up to positive square root of 1 minus x squared minus z squared. So there it is. So we've set up our thing. Those are the limits of integration. So these outer limits of integration are just like setting up a double integral. And then you want to know, like, how low do I start and how high do I get? Something like that. Well, what a mess. Do you want to compute this? No, right? Like, I don't know. I mean, that was a leading question. I didn't think you wanted to compute it. But, because this looks like sort of a mess. Even if you were to integrate this, to be able to integrate this with respect to y, then you'd have to put these in as your limits of integration. Then you have to integrate that with respect to x. What a mess. But it's carefully contrived to be easy. Okay, so let's have a look at this. So notice that this region R is symmetric with respect to y. So if you have if you look at y equals 0, the xz plane, the piece of it on the left, on one side of that, is the same as a piece of it on the other side. Like the y equals 0 plane acts as a mirror for the surface. Yeah, you can see, like, it would be the quarters ball on this side and the quarter ball on the other side. Okay, so R is symmetric with respect to y. And then let's look at this function. So maybe, yeah, I'll look at it here. Suppose you put in some value for y, like y equals y. You would get some number. Now suppose you put in negative y, like the opposite of the same thing. Well, cosine, or if you put in the point x comma y comma z, you would get something. Now suppose you put in the point x comma negative y comma z. Well, cosine of x times negative y is the same as the cosine of x times y, because it's the x value of something. So if you put in a negative angle, the x value of that thing is the same as if you had put in the positive angle. They're the same. So cosine of negative xy is the same as cosine of xy. This thing has nothing to do with y. So you put xz, and again, you get the same thing. And this thing changes sign. So whatever crazy, weird, horrible value this is, on one side of the ball, it'll be equal and opposite on the other side of the ball. So actually, this whole part integrates to 0. Over this particular region. Now, if we had integrated this over some other region, it wouldn't have integrated to 0. But because our region is symmetric with respect to y, and this function is odd with respect to y, it integrates to 0. Crazy, right? So, let me just get rid of a little bit of this. Okay. So this whole integral is equal to the triple integral over the region, and I'm not going to write the limits of integration again because they're right up there, of just 3 dv, because we had plus 3 here. So this integrates to 0 part stops there at the crazy function. The 3 was not related. So it's just integrating 3 over this region. We know if we integrated 1 over the region, we just get the volume of the region. So here we just get 3 times the volume of the region. So this is 3 times volume of R. So now I have to figure out what that is. So it's 3 times Well, if it were a whole ball, it would be 4/3 pi times 1 cubed, because the radius is 1, but it's only half of that, because it's a half ball. And the 3 cancels out, the 1 cubed is 1, 4 cancels with part of 2, so it's just 2 pi. Whoa, amazing. Yeah? Yeah. If we triple integrated 1, why would we get the volume? Yeah, so if we triple integrate 1, it's just like saying the density is 1 everywhere. What is the total mass? Sort of like in double integrals we talked about the other day. If you take the double integral of 1, you're finding the volume of a solid with height 1, which just gives you the area of the base. So it's exactly the same idea, but 1 dimension up. Just like if you do a single integral of the function 1, it just gives you the length of the interval you're integrating over. Then in double integrals, you integrate 1, you get the area of the region you're integrating over. Triple integrals, you integrate 1, you get the volume of the region you're integrating over. Yeah, so that's that. So this was carefully contrived to be an odd function with respect to y over an integral that was symmetric with respect to y, so that it integrates to 0. Such a clever trick. So you should look out for this, especially if you integrate something and it comes out to 0 and you're a bit surprised. You might look at it and think, oh, I wonder if the function was actually symmetric or an odd function over a symmetric region. Maybe that's why. Be kind of nice. Yeah, good question. Other question? Yeah. Okay. Okay. Okay, so now we'll work on setting up integrals again. So, more integrals. So, for instance, find the volume of the region bounded by the coordinate planes and the plane 3x plus 2y plus z equals 1. 6 equals 6. Yes, that one comes out much nicer. Okay, so the first thing to do is to draw a picture. Always. Always, no matter what. So I would draw the 3 coordinate planes, the coordinate axes. So here's x, y, and z. So you'll notice that here I made x sort of coming out to the left and y going to the right, where over here I kind of made them both going to the right. Either way is okay. You'll notice that in both cases we follow the right hand rule. So if we take our fingers, put them in the direction of x, bend them toward y, our thumb points toward z. Over here, again, you have to kind of turn around, but if you put your fingers toward x, you bend them toward y, your thumb points toward z. So it's all the same. We just took this one and kind of rotated to the left to get this one. And if you can imagine the thing that you're plotting in your head before you draw it, you can think of which way maybe is a better way to draw the thing. And you might draw it in one way and then think, this isn't so great, and then switch it to the other way. Okay, so let's find some points on this plane. So I like to make my life easy by making things 0. So if x and y are both 0, I get z equals 6. So I have this point up here at 6. If x and z are both 0, I get 2y equals 6, so y equals 3. It's approximately here at 3. And the same idea, I get x equals 2. So the plane is an infinite plane, but the part that is in the first quadrant looks like this. First octant looks like this. So here's the plane. There it is. And we want to know what's the volume of that region there. Okay, so way 0 to do this is just geometry. So the volume of a pyramid is 1/3 area of the base times the height. So let's see. So here that's 1/3. The area of the base. This is a triangle that has base 2 and height 3. So the area of the base is 3 down here. So 1/3 times 3 times times the height is 6. So that's just 6. Okay, so we expect to get the volume of this thing to be 6. So let's try it using double integral. So double integral, you could do any of the 6 orders. Oops, triple integral. In the order, let's try dz, dy, dx. Okay, so dz, dy, dx means x is on the outside. So we're going to want to set up something like x equals something to x equals something. And then next is y equals something to y equals something. And then next is z equals something to z equals something. And then we just want to find the volume. So we'll integrate 1 dz, dy, dx. So our goal is to figure out these limits of integration first, because this is something familiar that we've done. We've done double integrals. It's just setting up a double integral region. So I'm going to take this part and draw it out here. So here's x and y. And then this region here, let's draw it here. So y was 3, x was 2. So there's the region there that we want to describe down here. X is 2, y is 3. Okay, so if we're figuring out y, x is a constant, so we pick our favorite x. Maybe it's this one, and do a vertical slice. So our y's go from y equals 0 up to y equals, 3 minus 3 over 2x. How did you figure it out? Yeah, like a line. So the y-intercept is 3, so it starts at 3. And then the slope is negative 3 over 2. That's how it got down to 2 in 3 steps. Okay, so this is this equation of this line, which is exactly how high y gets. So y here goes from y equals 0 up to y equals 3 minus 3 halves x. Okay, and we want all these vertical pieces going from 0 up to 3 minus 3 halves x, from x equals 0 up to x equals 2. So x goes from 0 to 2. Okay, great. So that's setting it up just like in a double integral. And now we have to figure out which z's we want. So we pick a point in the xy plane, maybe this one, and we want to figure out which z's we need. So drawing this picture in perspective up here, that point is there. So if you imagine something parallel to the z-axis, it would start somewhere far away, going parallel to the z in the positive direction. Ooh, now it enters the solid. It stays in for a while, and then at some point it pops out, and now it's out. So we want to know, where does it come in and where does it come out? So I think it's pretty clear. Here it comes in at z equals 0 in the plane, and then it comes out here as z equals something else. This plane, I guess. So somehow we have to take the equation for this plane and solve it for z. Hey, so let's do it. So here z is 6 minus 3x minus 2y. So we can put that in here. Z equals 6 minus 3x minus 2y. Okay, so z goes from 0 at the bottom, chink, in, to 6 minus 3x minus 2y at the top. 6 minus 3x minus 2y. There we go. Now it's all set. Okay, good. Did we get it right? We did. Okay, so now as some practice, let's compute the thing. Okay, so I'm going to compute this up here. So I'll just copy the outer integrals. We go from x equals 0 up to x equals 2. We go from y equals 0 up to y equals 3 minus 3 halves x. Okay, and now let's do this part. So we do integrate 1 with respect to z. Okay, and then we plug in z equals this minus z equals that. So we just get this as our integrand. So we get 6 minus 3x minus 2y, and then we're integrating that dy, and dx. Okay, and now it's a familiar double integral. Now we just have to do it. Okay, let's do it. Copy the outer integral, x goes from 0 to 2. And now we're going to integrate with respect to y. 6 with respect to y. 6y. In fact, okay, fine, 6y. 3x with respect to y. Minus 3xy. 2y with respect to y. Y squared. Minus y squared. Okay, we do that whole thing and plug in from y equals 0 up to y equals 3 minus 3 halves x. We do that whole thing dx. Okay, and then since you're going to have to plug in for y and y squared here, life is going to get messy and bad, but not difficult, just messy and bad, in a way that would make people fall asleep if you weren't outside and it were already 50 degrees. So we'll omit that and just let you know it does work out and you get 6, which is what you wanted. Because we computed at the beginning that by basic geometry that the volume of this pyramid was 6. So it should come out to 6. And indeed, if you're careful and you don't make too many mistakes, and then you find your mistakes, you get 6. Yeah. Okay. Questions, ideas? Okay. Right. Good. Good. Oh yeah. Okay. Okay. So the thing that we've been doing so far today is that we were given a region, like maybe a picture of the region or some kind of description of it, like this, and then we were asked to write down the bounds for the triple integral. So a different thing you could wonder is, like, suppose you're given a triple integral like this. Could you figure out what the region looks like? Probably. So let's do it. Okay. So, describe the region of integration for the integral, okay, 0 to 1, 0 to square root of 1 minus x squared, and then 0 to square root of x squared plus y squared of some function f of x, y, and z, whatever it is, and then dz, dy, dx. Okay, so when I get an integral like this, I'm like, I don't know what's going on. I need a little bit of help here. So when I write out my own integrals, I always say something equals something to something. So like I always have variables on it. So I'd say that that's the first thing to do. So the outer integral is x. So we're going from x equals 0 up to x equals 1. And then the middle one is y. So we're going from y equals 0 up to y equals root 1 minus x squared. And then the inner integral is z. So we're going from z equals 0 up to z equals square root of x squared plus y squared. Okay, now we have some chance of ever figuring out what's going on. I recommend doing this. When you get integrals given to you, like in a book or something, they will not have generally these equals, but I suggest putting them on right away so that you can figure out what's going on. So this I call like the shadow plane, and maybe we want to figure out which region we're integrating over in the, as it turns out, xy plane before we go on. Okay, so in the shadow plane, which is the xy plane, here it is. We're going from x equals 0 to x equals 1. Okay, so x equals 0 to x equals 1. And then we're going from y equals 0 to y equals square root of 1 minus x squared. So I suggest graphing these things. So y equals 0, that's just a horizontal line, y equals 0. And then y equals square root of 1 minus x squared. Y equals square root of 1 minus x squared. You might immediately recognize what it is, or you might not, so we could just figure out what it looks like. So maybe square both sides. Y squared equals 1 minus x squared. and then put the x squared on the other side. X squared plus y squared equals 1. Ah! I know what this is. Now I know what it is. This is a unit circle. Okay, so unfortunately, when you do it in this order, it means you have to draw your circle second, which violates a principle of mathematics, which is always draw your circle first and then draw your axes. But it's okay. Okay, so we want to go from y equals 0, that's this, y equals 0, up to y equals square root of 1 minus x squared, from x equals 0 to x equals 1. So we're making like these, all these little vertical things here. So we're integrating over this region. Okay, hey, we got it. So that's the first two parts, and then we just have to figure out what's going on with the z. So let's figure this out, maybe in another color. So z equals 0 up to z equals square root of x squared plus y squared. Okay, I know what z equals 0 is, that's just the xy plane. But this one here, z equals square root of x squared plus y squared. Do you know what it is? We could square both sides. Z squared equals x squared plus y squared. So we did talk about it when we talked about quadric surfaces. It's like the limiting value of the two-sheeted and one-sheeted hyperboloids. So you'll notice it doesn't have a +1 or a -1. Also, one thing you can see is like, suppose y equals 0. Then you get z squared equals x squared. So z equals plus or minus x. Those are just two lines. The same if you make x equal to 0. Z equals plus or minus y. So the cross section of this thing is lines. So the cross section, let's see, of this thing is lines. Okay? And then if you set z equal to a constant, like 1, you get circles. So when z equals a constant, you get circles in these directions. So these are circles. So it's a cone. Okay, so this is a cone. Okay, so I'll just draw a cone. Here, there's the cone. Okay, and then here is the xy, the shadow of it in the xy plane. And then we wanted to go just in this little region here. So I'll draw this in some kind of perspective. So maybe that's here. So here's the positive x-axis, here's the positive y-axis, and there's the region that we're integrating over. And then for each point in the xy plane, like maybe this is our favorite point here, it says we need to go from z equals 0 up to the cone. So our point comes in from negative infinity. It pierces the solid at the plane. It stays in the solid until it hits the cone, and then it's out of the solid. So it means that the solid we're integrating over is the part below the cone. Can you imagine that? It's like you have a cone inside a cylinder, and you want everything that's outside the cone but inside the cylinder. So I'll try to draw that. Right. So here's the part of the cone that's inside our thing. And it's this whole solid region here. There it is. So there's a region we're integrating over. There. Describe the region of integration for that thing. It's below the cone and above the xy plane. Yeah. Questions or ideas? Cookies? Okay. Good. Yeah. It's kind of fun actually to sketch the integral. It's like a puzzle, like someone describes something and you get to put it together. Okay, so let's try one more. So, sketch the region of integration. For the integral 0 to 1, root x to 1, 0 to 1 minus y, f of xyz dz dy dx. Okay, this is our quest. So again, I think the first thing you should do is label what all these things are. So this is going from x equals 0 up to x equals 1. It's going from y equals root x up to y equals 1. And it's going from z equals 0 up to z equals 1 minus y. So now we maybe have some chance of figuring out what's going on. Okay, so let's first consider this shadow plane, the xy plane. So what is the shadow of our region in the xy plane? Let's do it. So over here, I'll draw the xy plane. How much of it do I need? Not that much. Okay. We want to go between x equals 0 and x equals 1 again. So 0 and 1. And then we want to go from y equals root x up to y equals 1. So y equals 1 is this line. And then y equals root x, well, it's like a sideways parabola. Yeah, it's like essentially x equals y squared. So it goes through the point 1, 1, and the bottom of the parabola is here. So it would keep going like this. There's the parabola. I didn't quite hit the point, so I'll move the point. There. Okay, and so for each x value, we are entering at y equals root x and exiting at y equals 1. So we get this region here. Okay, great. So now we know our shadow plane thing. Now let's draw this in 3 dimensions. So here's x, y, and z. I think it's helpful sometimes to make yourself a rectangle because it's easy to draw rectangles in perspective. So our whole thing is inside this 1 by 1 square. So now over here, I'm going to draw the same 1 by 1 square. And now I know everything has to go to the point 1, 1. And in the top is the line y equals 1, which is this line. So here's 1 and here's 1. And then it's a parabola where like the tangency point was at 0. So the parabola is like this. Okay, so that's one way of doing it. And we wanted vertical lines. Okay, so I've taken this region and I've drawn it in 3D. So whatever my shape is, it's going to be over this thing. Okay, now the last thing to do is to figure out this z part. So z is going from z equals 0 up to z equals 1 minus y. Okay, z equals 1 minus y. So here I have the yz plane in the back. It's actually quite easy to see here, just in the back. And z equals 1 minus y is just a line that starts at z equals 1 and has a slope of negative 1. So z equals 1 minus y just looks like that. And it doesn't have x in it at all. So it's the same for all the x values. So it's just a plane. It's just like if you take this line and you just move it out towards us in the x direction. Okay, so for sure, 2 faces of our solid thing are this yellow part on the bottom and then this sort of orange back part, which I'm not going to shade in, but it's the back. So then we have to figure out like what's the rest of it. So the idea is we have to figure out where this curve, okay, so think about this curve not as just a curve, but actually as a whole curved vertical thing. So you call it a vertical cylinder over something, even though it's not like a round cylinder, it's just like a cylinder. Cookies? Sure, right? Okay, and we want to figure out where that slices through this plane. So let's see, let's do that. Okay. So we know, let's see. So we need to figure out where the plane z equals 1 minus y intersects the surface y equals root x. And okay, so how do we do this? So one way you could do it is just find some points on it. So for instance, you could find where this intersection, so a plane intersecting surface is going to be a curve. So we want to know some points on the curve. So in the, let's say, YZ plane, x equals 0. If x equals 0, well, y equals root x. So y equals 0 because y equals root x, so root 0, which is 0. And then z is 1 minus 0, which, because that's y, which is 1. Okay, so this gives you the point x equals 0, y equals 0, z equals 1. So this point, 0, 0, 1, let me make it red, is on the intersection curve, for sure. Okay, how about in the xy plane? Z equals 0, that defines the xy plane. So 0 equals 1 minus y. So y equals 1. And then y equals root x. So 1 equals root x. So x equals 1. So this gives us the point x equals 1, y equals 1, z equals 0. So that gives us this point. So I put those on here in red. So those 2 points are on our curve. And then our curve connects these points. So now is the time where you just imagine what it looks like in 3 space. So you have this curved surface. You can imagine this yellow curve just like moving up and down like a cookie cutter. And then you have this plane coming through. And somehow they intersect. And the way they intersect is like something like that. So maybe one way to see this is for me to sketch in the other 2 faces of the picture. So the front is the curved surface on y equals root x, like that. And then the top is like this roof formed by the plane z equals 1 minus y. Can you see it? I think so. Maybe the bottom is confusing with the shading of the base, but you get the idea. So it's kind of like a curved tetrahedron. And that's it. Questions or ideas? So it's kind of fun. You're given these numbers or curves or whatever, surfaces, and then you have to figure out how to put them together to get a solid, like what they look like. Yeah. Okay. That's it. Thank you.